Since the mid-1980s, the falling weight deflectometer, or FWD, has become an indispensable tool for pavement engineers. Engineers use the information provided by FWDs to predict a pavement's expected life and then decide how best to maintain that pavement. To produce this valuable information, an FWD measures a pavement's response to a load. When the FWD lowers its load plate and drops its weight, it's simulating the load that vehicles put on the pavement every day. That constant loading can be a major cause of pavement deterioration. The pavement responds to the FWD's load by bending downward, or as we say, the pavement deflects. If you stand near your FWD when it's working, you feel the deflection. It's not subtle. The FWD's sensors measure the deflection. Naturally, the pavement deflects most at the center of the load and less farther away. We call the depression caused by the load a deflection basin. Each sensor produces an electrical signal in proportion to the deflection it measures, and the signals from all of the sensors go to the computer where the data is stored. Since your FWD is so crucial to the design and maintenance of pavements, it's essential for it to produce reliable data. To do that, all of its important components, weights, buffers, load cell, sensors, the hydraulic, electrical, and mechanical systems, and the computer hardware and software have to work right. But there are lots of reasons why your FWD might not produce reliable data. For one thing, there could be a problem with the sensor. A sensor might get damaged, or it might just be worn out after years of use, or its cable might get broken. Obviously, you want to know about any problems like this as soon as possible so you can avoid producing unreliable data. The way you find out is by calibrating your FWD. That's where the LTPP project comes in. LTPP stands for Long-Term Pavement Performance. It's a research project that began as part of the Strategic Highway Research Program called SHARP. SHARP has been completed, but LTPP continues. It's run by the Federal Highway Administration with cooperation from transportation departments in every U.S. state, Canadian province, and many other countries. One important product of these programs has been a set of standardized FWD calibration procedures. You can do part of the calibration procedure anywhere, and you should do it often to be sure you're gathering good data. We'll come back to this in a few minutes. But there's another part of the procedure that can only be done at a calibration center. 4 regional calibration centers have been built as part of SHARP and LTPP, and every FWD needs to go through both parts of the procedure at least once each year. So that's why you're going to the calibration center. But hold on, there are things you need to do before you go. When you get to the calibration center, you and the calibration center operator will be able to go through the calibration process in 6 or 7 hours if you arrive ready to do the job. Everything you need to know about getting ready is in this booklet and is summarized in this pre-trip checklist. Let's take a walkthrough of everything you need to do. First, be sure all connections, fittings, and cables on your FWD are in good repair. If your load plate swivels, lubricate the swivel. Be sure you have a 12-inch diameter load plate installed, and for some types of FWD, torque the bolts to specification. Clean all of the sensors. When you get to the calibration center, you'll need to take the sensors out of their holders. Be sure your printer is in good working order and that you have an extra ink cartridge and a good supply of paper. If your FWD has been to the calibration center before, be sure the diskette containing the last set of calibration results is in your van. If this is your first trip to the calibration center, bring a blank formatted diskette with you. Also, be sure your FWD manuals and the most commonly needed spare parts are packed in your van or trailer. The calibration centers are not FWD repair garages. They don't stock spare parts. Test all of the batteries and clean the terminals. Bring a calibration stand that can hold the maximum number of sensors used on your FWD. If you don't have a calibration stand, you have to get one from the manufacturer. check the hydraulic system for leaks, and perform any needed maintenance. Finally, program your FWD so it's ready for the test. Detailed instructions are in the booklet entitled Guidelines for Users of the Sharp FWD Calibration Centers. That's a lot of tasks and a lot of details, so use the checklist in the booklet to be sure you get everything done. Okay, now you're ready to hit the road. For the next part of the calibration process, we'll be looking at a different type of FWD. Hey, here it is now, pulling into the calibration center. Before you begin calibration, it's important to let your FWD's components stabilize at the temperature inside the calibration center. That's especially important for the buffers and the hydraulic system. So, if you're traveling in cold weather, you should arrive a day ahead and leave your FWD overnight in the calibration center garage. In the morning, just before you begin the actual calibration process, the calibration center operator will ask you to run your FWD through quite a few drop cycles. You do this to flex and warm up the buffers, like an athlete warming up for an event. Now, before going through the calibration process, let's stop and think about why you calibrate an FWD. The goal is simple: quality. You calibrate your FWD's sensors to find out if they're putting out accurate data. Manufacturers guarantee that, barring physical damage, sensors will be accurate to within plus or minus 2% of actual deflection values. But with calibration, we get much closer than that. Here, we're representing FWD data with these waveforms. Each waveform represents data gathered by one sensor. In the first part of the calibration process, called reference calibration, we compare each sensor to an accurate standard, our reference, and correct for the error in that sensor's output. Now, the standard can't be perfect, and neither can the process of comparing the sensors to the standard, but there's still a way to get more accuracy. In the second part of the process, called relative calibration, we put all the sensors in a special holder that makes sure they deflect the same. Then we measure the output of each sensor many times and average the outputs. The average deflection is more accurate than the output from any single measurement. The result of relative calibration is an additional set of correction factors that improve the accuracy of the data even more. Now, let's see how this actually happens at the calibration center. The first part of reference calibration is to calibrate your FWD's load cell. The calibration center has a reference load cell that's calibrated annually to a national standard. Working together, you and the calibration center operator position your FWD's load plate right on top of the reference load cell. Then you go through a series of drops at 4 load ranges. You compare the output of your load cell with the output of the reference load cell. The result is a gain factor, a number that you key into your computer. From now on, every reading from your load cell will be multiplied by this gain factor. The next part of reference calibration is to calibrate each of your FWD's sensors. As we showed earlier, a sensor's job is to measure the deflection of a pavement under a load. In this part of calibration, you compare the sensors, one at a time, with a very accurate device for measuring deflection called a linear variable differential transducer, or LVDT. But before the calibration center operator can use the LVDT to calibrate your sensors, we have to calibrate the LVDT. The LVDT is placed in a micrometer fixture and is connected to the calibration center computer. Working with this test rig, the operator and the computer determine how many computer bits it takes to equal a movement of 1 micron in the LVDT. A micron is a millionth of a meter. So that in the next step, the movements of the LVDT will be accurately translated into computer data. When the LVDT is calibrated, the calibration center operator puts it into a special fixture on the end of this aluminum beam, and he puts the sensor to be calibrated in a holder. The aluminum beam and the big concrete block it's attached to are designed to isolate the LVDT. That way, the LVDT can provide an accurate deflection measurement almost completely independent of the impulse that comes through the floor and up into the beam. But it's impossible to totally isolate the LVDT. So, the system is also designed to delay the deflection impulse from reaching the beam until the deflection has already been measured by the LVDT and the sensor being calibrated. To be sure there has been a delay, a second sensor is placed here at the end of the beam. Then you compare the timing between the second sensor and the sensor being calibrated. You can see the time delay on your computer. You go through a series of drops to compare each of your FWD sensors to the LVDT. Then the calibration center computer calculates a gain factor for each sensor, which you key into your FWD's computer. That's the end of reference calibration. Now we'll use a third type of FWD as we take a look at the next phase, relative calibration, where you arrive at even more precise correction factors for the outputs of your sensors. In relative calibration, you put all of your FWD sensors in the test stand that you brought to the calibration center. As we discussed before, the idea is that with all of your sensors stacked up in the stand, they can all measure the same deflection all at the same time. You hold the stand upright on the deflection pad while your FWD goes through a series of drops and your computer records the deflections. Then you move the bottom sensor to the top and all the others down one position and do another series of drops and so on until you've gathered data from every sensor in every position. As you're doing the relative calibration, it's very important to insert the sensors properly in the stand, hold the stand in the same location for all tests, and apply consistent pressure on top of the stand. After you run the tests, the computer analyzes the data to see if the data is valid, and it should be if you've done everything right. If there is a problem with the data, you may need to redo the relative calibration. As in the other phases, the result of relative calibration is a set of gain factors, which you enter into your computer. You'll take home a disk containing all of the test data and your new gain factors. Because relative calibration requires no special equipment besides the test stand, you can do it at your home garage or anywhere else, and you should do it often. It allows you to catch problems and avoid gathering days, weeks, or months of bad data. That's why your agency should establish a policy of doing this relative calibration regularly on all FWDs. LTPP's policy is to do it monthly. When you complete the relative calibration, you're done. But we've gone through a lot of information here, so let's quickly review the calibration process. First, you prepare before you leave for the calibration center by going through the pre-calibration checklist. If it's cold outside, plan to arrive at the calibration center the night before so your FWD can stabilize at the temperature inside the calibration center garage. When you begin calibration in the morning, the first thing is to compare your load cell with a reference load cell. Then you compare each sensor with the LVDT. Together, calibrating the load cell and calibrating the individual sensors make up the reference calibration. Then, in relative calibration, you compare your sensors with each other. The results of the calibration process are gain factors that you key into your computer. Those gain factors make sure the data produced by your FWD is very accurate. And accuracy is the whole idea of calibration. Accurate FWD data is essential to the LTPP project and to all pavement research, pavement management, and pavement design. So work closely with your regional calibration center and get out there and calibrate those FWDs. It's the right way to do business.